Welcome my friends, welcome to my next lecture. Now in my last lecture I was talking about the notions of curves. In fact I have introduced the definitions of curves. Now for today's lecture my plan is to talk about there are various types of curves like simple curves, simple closed curves, then you'll have a Jordan curve, then you'll have a Jordan curve theorem, then I will talk about the definitions of contour, and then we will have the notions of what is called contour integrations. Okay, so that is the plan for today's lecture, and then once I have a contour integrations, then I'll talk about what is called path independency, and then one of the fundamental theorem in complex analysis, that is called Cauchy-Goussat theorem. Okay, so as I said, so I have discussed the notions of curves. Let me just recall once again. So a curve is a continuous complex valued functions defined on the interval subset of real line. So that is, a curve is a continuous functions defined on subset I, subset of R, where I is an interval or it could be full real line. Three examples I have given. One is circle, another is straight line, another is parabola. Now once I have the definitions of curve, then I will talk about what do I mean by simple curve. Simple curve means a curve which is injective except the endpoint. Look, so that's what it is. So a curve gamma which is parameterized by, as I said, if I have a curve and if I define that curve by gamma, sometimes gamma is called the parameterizations. So a curve gamma, which is gamma of t, so gamma of t, or gamma is a map from closed interval AB to C, gamma t is said to be simple curve. Of course, it is continuous by definitions of curve. Simple curve means it should be injective. That means gamma of t1 is not equal to gamma of t2, if A1 lesser equal to T1, strictly less than T2, lesser equal to B. So that means if I take T1 and T2 from the interval say A to B, okay, but T1 is not equal to T2, okay. So if this is the case, then I will say that means what? That means I'm considering 2 points T1 and T2 from interval A to B where my gamma is defined. If T1 not equal to T2, then gamma of T1 not equal to T2. That means I'm talking about my function is injective, okay. So except possibly, okay, as I said, so except possibly the endpoint. That means if T1 is equal to A and T2 is equal to B, then I could assume that my gamma A can take the same value with gamma B. So except the endpoint, so that means you can say that T1, T2, if I take open interval A to B, T1 not equal to T2, then I'm saying that my gamma is taking, that means gamma of T1 not equal to gamma of T2. Okay. So that means my function is injective except the endpoint. That means if T1 is equal to A, T2 is equal to B, it might happen that gamma of A is equal to gamma of B. But except the endpoint, if I take any T1 and T2 2 points from the interval A to B, and if T1 not equal to T2, then I demand that gamma of T1 should be not equal to gamma of T2. That means it should be injective. Look, so that is, a simple curve is a curve that does not cross itself. Okay, that actually implies this one. Does not cross itself means what? Look at this picture. Okay, suppose you have a gamma. So suppose this is my curve gamma. Okay, that means gamma is a map from closed interval AB to C, which will have this kind of picture. Like in my earlier slides, I talked about that various curves like circle, straight line, or parabola. Similarly, if gamma is suppose this is a curve, then it will have a parameterization, so it will have a definition. That means you have a gamma. That means this represents a function's gamma from some closed interval AB to C, which is continuous. Now look, so if that means what? This is a continuous function. That means if I start from here, let me let it be gamma A, right? And it will end up at here. That means it should be say gamma B, okay? But now look, there is a cross, okay? So that means now if I start from A and moving towards B, that means it will at some point in the interval, suppose this is A and this is B. So I'm starting from A, that means I'm starting from here, then I am going in this direction, that means I am moving in this curve along. So we will have 1 point, so that means at some point of time, so let it be T1 here, this is my T1, so this value will be gamma of T1, right? Then what? Then again I am moving in this direction, then I'll move along the curve, then again you will have the same value because it crosses, right? So that means at same point I will have another point, say let it be T2, suppose this is my T2, then you will have the same value, so this is gamma of T2 because this crosses is there, right? So therefore I have T1 which is not equal to T2, right? But still I have the since it crosses, so therefore gamma of T1 is exactly equal to gamma of T2 because once I have this value, then I will move again, I will reach at the same point. So therefore, I have two distinct points T1, T2 in the domain, but I will have the value gamma of T1 is exactly equal to gamma of T2. It what is called contradicts the definitions of simplicity or simple curve. So therefore, my function is not simple. So therefore, if there is a cross in my curve, my curve is not simple. Similarly, if there is a what is called 8 figure, this is called 8 figure, it looks like this 8. So that means there is a cross, right? If there is a cross, that means if I start from here, again along the interval A to B, if I move, so if I move in this direction, one time I will reach this point, again if I go back, so I'll another point. So I have two different T1, T2, but the corresponding value will be same. So therefore, my function or curve is not injective. So that is why I've written that is a simple curve is a curve that does not cross itself. If it crosses, that means I will have the existence of two distinct points T1 and T2 in my domain, such that the corresponding value gamma of T1 is exactly equal to gamma of T2. That means it breaks the injectivity. So therefore, my function or curve is not simple. Okay, so example, for example, circle gamma of t is equal to e to the it. Of course, it's a simple curve, because if you look at the picture, so circle looks like this one, na? So therefore, if I start, say suppose gamma of t e to the power it, t runs from 0 to say 2 pi. So what will happen? T is equal to 0, then it will start from here, right? And then what will happen if t runs from 0 and moving toward 2 pi, then it will move along this path, and at this when t is equal to 2 pi, it will same. That means gamma of 0 is same as gamma of 2 pi. But you see, in the definition I say that in the end point I don't care about the injectivity, but I do care if I take 2 points in the interval open 0 to 2 pi. But if open 0 to 2 pi, as long as t1 and t2 are two distinct points in open interval 0 to 2 pi, it is going in this direction. That means it is always taking two different points. That means it is always injective. So therefore, my functions gamma of t or curve gamma of t is equal to e to the it, which is actually a simple curve. Similarly, if I take the straight line, suppose again this is my z1, this is my z2, right? So the straight line is this one. So again it is a map from 0, 1 to c, and what is the equation? T z2 plus 1 minus t z1, right? Again, so if t is equal to 0, it is start from what? Z1, right? And if t running from 0, if it goes to 1, so it will take all the points here and end up in J2. So at each point t in between, if I take two distinct points, he will have two distinct values. So therefore, this function is injective. So therefore, my curve is simple curve. Okay, so this is simple. So therefore, I have written the circle, the straight line, or the simple curve in the complex plane. Now look, there is a note: any curve of the shape of number 8 is not simple curve. I just explained. So if it crosses, so I will have the existence of two distinct points in my domain, either could be R or in the interval A to B, so that the corresponding value gamma of T1 is exactly equal to gamma of T2. That is, when cross figure or 8 figure will be there in a curve, means my curve is not simple. Closed curve means what? Closed curve, from the definition it clear. So if I have a curve, then it will have it will be a map from closed interval AB to C, or it will have a parameterization, let it be gamma. Closed means what? So the value of my gamma at the starting point, it should be exactly same as the value of my gamma at the end point. That means if my gamma is a map from closed interval AB to C, gamma of A should be exactly equal to gamma of B. That is called the closed curve. Okay. So definitions: a curve gamma is said to be closed if the value of gamma at the initial point is exactly equal to the value of the gamma at the final point. So gamma of A is equal to gamma of B. So for example, circle. If I take a map from 0 to 2 pi to C is like gamma of t is equal to e to the power it, that is a closed curve. Why? Because at t is equal to 0, it is taking the value 1, and at t is equal to 2 pi, again it will come back and same value. So therefore, this is a simple closed curve. Straight line is not a closed curve, because if I have Z1, if I have Z2, so it will be a curve Z1 to Z2. But if Z1 is not equal to Z2, so therefore gamma of 0 is not equal to gamma of 1. So therefore, it is not closed. So the circle is a closed curve. The oriented boundary of a rectangle also. Okay, that is also true, because suppose this is my rectangle. Oriented means what? So if I start from here, if I go here, then they go there, come back here, and then come back. So therefore, oriented boundary, it will be a what is called closed curve. The line segment gamma is not closed. Of course, as I said, if I have two distinct points Z1 and Z2, gamma of 0 is not equal to gamma of 1. Similarly, if I have a parabola, so two endpoints are different, so it is not a closed curve. But circle is a closed curve, or oriented boundary of a rectangle or triangle, it is also closed curves. So for example, these are kind of example closed curve. So if I start from here and come back and reach here. If I start from here then I'll go and come back here. This is not closed because if I start from here, I'll go and I'll come back here. So these 2 points are different. It is not a close. If I start from here, by parameterizations, I'll have reach here, but these two things are different. So therefore, this curve are not closed curves. The definition of what is called simple closed curve, that is called Jordan curve. Now, simple closed curve means what? You know the definition of curve, you know the definition of simple curve, and you know the definition of closed curves. Simple closed curve means it is a curve, it is simple as well as it is closed. So definitions: a curve gamma is said to be simple closed curve. Sometimes it is called what is called Jordan curve. If it is closed, that means if value of my functions gamma at the initial point and at the final point should be same, and it should be injective if I take 2 points T1, T2 from the open interval AB such that T1 not equal to T2. One of the simple example of Jordan curve or simple closed curve is the circle. Because circle, if I take these parameterizations, gamma is a map from 0 to 2 pi to C, gamma of T is equal to e to the power IT. Of course, as I said, gamma of 0 is equal to gamma of 2 pi. It both value will be same, it's 1, 0. It is injective because if I take any 2 points from the open interval 0 to 2 pi, it is injective. So therefore, it is a simple closed curve. So therefore, it is a Jordan curve. Straight line, it is simple, but it is not closed. Okay, so therefore, it is not a Jordan curve. Okay, if I have a curve of say crosses 8, so crosses 8 means what? It breaks. It is not simple. So therefore, it is not Jordan curve. This curve gamma t, it is a simple curve because it is of this kind of figure, but it is not closed, so therefore it is not Jordan curve. So these are the example of Jordan curve. So for example, it is injective from the picture is quite clear. It is injective as well as it is closed. It is a Jordan curve. This is Jordan curve, but these are non-Jordan curve because it is not closed. This is not closed, not closed. This is what? Not closed as well as not injective or not simple, I should say. And simply this is what? This is closed curve, but it is not simple. Okay. So Jordan curve or simple closed curve mean the curve should be simple as well as it is closed. Okay, a couple of examples I have given. For example, this is the one, a curve that is simple curve because I am starting with a point ZA and moving and I am ending at the point ZB, but it is injective because there is no cross is there, but it is not closed because ZA is different from ZB. So it is a simple curve, but not closed. This is a simple closed curve because if you start with ZA, then I am moving in these directions and it is not crosses, so it is simple. At the same time, value of Z at A is same as value of Z at B, so therefore it is simple closed curve. Now this is the curve where you see crosses are there, so therefore it is not simple, as well as ZA, the initial value and the final value, these two are also different, so therefore it is not simple, not closed. And what about this one? So this is ZA is equal to ZB, that means it is a closed curve, but there is a cross. At this point, what is called my curve injectivity breaks, that means my curve is not simple. So therefore it is closed curve, but it is not simple. Now there is a famous theorem, what is called Jordan curve theorem. It says that if I have a simple closed curve, then I can break my domain into two parts. One is the interior part that is bounded by this simple closed curve, that is called the interior, that is the bounded part, and another part is the what is called complement, that means that is the exterior part, that is the unbounded part. Look, so Jordan curve theorem, it says that the points on any simple closed or curve or Jordan curve, suppose this is a simple closed curve, right? This is the one, simple closed curve. Any point on the simple closed curve or Jordan curve C are boundary points of two distinct domains. So this is one of the domain, this is the outer part, and the blue one is the inner part. So this is one of the domain, open connected set, this is also open connected set, and it says that what are the point on C? These are the boundary. That means it kind of distinguishes my exterior part, the interior part. So it says that the points on any simple closed curve, simple closed, I think this is closed, D is missing, okay, simple closed curve C are boundary points of two distinct domains. That means this is the interior domain, this is the exterior domain, one of which is the interior of C, that means this is the interior of C, and it is bounded, the other which is the exterior of C, and it is unbounded. This is the exterior of C, this is the unbounded part. So therefore, any points on any simple closed curve or Jordan curve are the boundary points of two distinct domains. One is the interior, that is the bounded domain, another is the exterior, that is the unbounded domain. Similarly, I have a simple closed curve, right? So this is my simple closed curve, okay, right? So you have two, one domain is the bounded interior, that means this is the green is one the interior and exterior is the white one. So interior is the bounded domain and this is the exterior unbounded domain, and this is the kind of boundary points of these points on the Jordan curve or simple closed curve. So sometimes this theorem is known as Jordan curve theorem. That means if I have a simple closed curve, it breaks my domain on the full complex plane into two parts. One is the exterior, another is the interior. Interior is the bounded domain, exterior is the unbounded domain. Now there is a parallel notion called differentiable curve. Now you can check curve means what? It is a map from some closed interval AB subset of R to C which is continuous. Differentiable means what? I need one more condition. That means my functions not only should be continuous but it should also be differentiable. That is called differentiable curves. So a curve gamma, which is of course this is the parameterization gamma, which is zt, which is xt plus iyt or xt comma yt, is said to be a differentiable curve if the derivative exists. That means if my functions x and y are differentiable, or my functions z or zt or gamma t, whatever it is, it should be differentiable. That means derivative should be exist. Not only that, I demand that it should also be continuous. So that means a map from closed interval AB to C to the complex plane, if my map is differentiable and the derivative is continuous, then those kind of curve is called what is called differentiable curve. Because curve means what? Curve means I just need the continuity, right? Differentiable curve means I need the function should be differentiable. Not only that, derivative should also be continuous. So that means this is kind of much more demand I need for the differentiable. That means it's very nice, I should say. Okay, so a curve gamma, of course by definition of curve means it is a continuous functions. So I need something more. That means I need gamma should be differentiable. Not only that, derivative also should be continuous. So a curve gamma is said to be differentiable curve if derivative exists, and not only that, it should be continuous. And again, the three simple example, one is circle, straight line, parabola. These are all differentiable curve. Why? Because gamma of t, which is cosine t plus I sine t. Na? So this is what? So this is the component xt and yt according to my definition. This is xt is cosine t, yt is sine t. And what is cosine t, sine t? These are what is called trigonometric functions, infinitely many times differentiable. So derivative exists and derivative is also continuous. So therefore it satisfies the definition of differentiable curve. So therefore circle, this is a circle, this is a differentiable curves. What kind of this function gamma? Again, it is a polynomial in t. It is also infinitely many times differentiable, and therefore if it is one times differentiable and derivative is continuous, so therefore this is straight line joining z1 to z2, that is also differentiable curve. Parabola, again, what is the xt part? Xt part is t. What is the yt part? Yt part is t square. Again, it is a polynomial in t. Both functions are infinitely many times differentiable, x and y. So therefore my functions gamma or z, this is also differentiable function. Derivative is also continuous. So therefore these are differentiable curves. That means I need more smoothness on my gamma. So that means for at the definitions of curves, I demand only the continuity, but differentiable means I need more smoothness. That means it is differentiable and derivative also should be continuous. So once I have a differentiable curves, then this is kind of notions you might familiar with. Okay, it says that how to calculate the length of the curve. It says that, of course, for example, if I have a circle, so what is the length? If it is a circle of say gamma t is equal to e to the power it, right? So what is the length of this curve? This is if it's circle of radius 1, that means it's 2 pi. So but there is a formula. If I have a differentiable curve, then you can have the formula for calculating the length of this curve. So it says that if gamma is equal to say zt is the parameterization, zt is equal to xt plus iyt, it is a differentiable curve, then length of the curve gamma from the point joining the point za to zb, so it starts from za and end at zb, right? Because this is the initial point, this is the final point. So from za to zb it will be a curve. So what is the length of the curve? So length of the curve, there is a formula which is nothing but integrations a to b absolute of z prime of t dt, because since it is a differentiable curve, z prime exists, right? It is differentiable, and this is also continuous. That means z prime is also continuous. So therefore modulus of z prime, that is also continuous functions. So therefore this integral makes sense, and that means this is nothing but integrations a to b square root of x prime t whole square plus y prime t square. So this is the formula. If I calculate the formula, then it will give you the length of the curve. So okay, so maybe one example I will calculate, it will be clear. So suppose C has a different. This is one point you should remember. So if I have a curve, it might happen that that curve will have one more parameterizations. For example, so if I have a differentiable curve, so this is the corresponding parameterizations. But maybe that same curve will have another parameterizations. But you see, the way I am giving the definitions of my length of the curve, so if I have a curve, So it will have a parameterizations, and in terms of the parameterizations I am giving the formula square root of x prime t square plus y prime t square. If I take the integrations of square root, then it will give you the length of the curve. Then you can ask, okay, instead of xt comma yt, if I take another parameterizations, let it be ut comma vt, and suppose it will give you the same curve. Will the same formula is independent of the choice of the parameterizations I can take? Answer is yes. So that's exactly I have written. Suppose C has different parametric representations, then also the value of the length of the curve is invariant. That means if gamma has a parameterization, so let it be zt, which is xt plus I yt, okay. So if t runs from a to b, okay. So whatever the value you will get, that means the integrations a to b, square root of x prime t square plus y prime t square dt. Suppose gamma will have another parameterization, so let it be say gamma, so let it be z twiddle t, say ut plus I vt, okay, and say t runs from say a naught to b naught, okay. So then by the same definition you can say that this is length of the curve gamma is same as integration a naught to b naught square root of ut square plus vt square, okay, dt. What I am trying to say is that this is same as, so this should be same as the value integrations a to b x prime t, oh yeah, so this should be u prime and this is v prime, yeah. So this is x prime t square plus y prime t square. So my point is that if I have a curve and suppose it will have two different parameterizations, the way I have given the formula, a priori it looks like it depends on the parameterizations, but one can prove that even if I work with two different parameterizations, but the length of the curve will be invariant under this parameterization. That exactly I have written. Suppose C has different parametric representations, but also the value of the length of the curve is invariant. That means whatever parameterizations I can use for the same curve, the length will be the same. Okay, so therefore it makes sense to give the length of the curve in terms of the parameterizations. Okay, so one example, as I said, you just calculate, suppose your circle. So zt is equal to, what is that? So zt, this is e to the power it, na? So t running from 0 to pi. So that means what? That means I have a 0 to pi, not 2 pi. That means I have a circle. So not full circle, but I will have a semicircle. It starts from here, it will end up here. So what is the like length of the interval? Then now you can say that this is actually pi, right? How to calculate it? So since I have a parameterization zt, calculate z prime t. This is minus of sine t plus I times cosine t. That means it is the so z prime of t is nothing but the derivative of the component. So component of cos t derivative is minus sine t, and sine t derivative of cosine t. What is the absolute? Again it will be 1, and length of the curve joining z is equal to 0 to z is equal to pi. That means it should be 0 to pi z prime t dt. That means 0 to pi 1. That means this is pi. And this is the semicircle of radius 1. What is the length? Length is actually length of the curve is pi, that you know. Okay, so that's the formula where you can calculate the length of the curve. Of course, my curve should be nice. That means it should be differentiable curves. Okay. Now I come to what is called smooth curve or regular curves. Okay, so smooth curve means what? So as I said, I need little bit more smoothness. So what is my definitions? A curve gamma, suppose gamma will have a parameterization zt, which is xt plus I yt, then it says that I am saying that this curve is smooth or regular. I need two kind of requirement. One is that my function should be, curve should be differentiable. That means derivative exists and it is continuous, right? On top of that, I need that derivative is also non-zero if t runs from a to b, open. So therefore, what is called smooth curve or regular curve means it is a differentiable curve, right? Of course, it is, that means smooth. That means it should be differentiable and derivative is continuous. That is okay. On top of that, I need that derivative should also be non-zero if t runs from a to b. Okay. So examples of smooth curve, again just go to circle, gamma t e to the it, right? So what is the derivative? Cosine t plus I sine t, right? What is the derivative? Gamma prime t, which is minus sine t plus I cosine t. So that is also non-zero, right? If t runs from open 0 to 2 pi. So therefore this is a curve what is called a smooth curve or regular curve. Similarly, you can say that line segment also is smooth curve, because if I take the gamma prime, so what is the gamma prime of this one? Gamma prime of t, what is that? You just calculate, this is nothing but z2 minus z1. This is constant, and z1 is different from z2, so therefore this is non-zero. So therefore this is what is called smooth curve. Similarly, if I have a parabola, that is also smooth curves, right? Because what is gamma prime of t? It is should be 1 plus I times 2t, and if t runs from r, so this is always non-zero. So therefore that is also a smooth curve or regular curves. Okay. So smooth curves or regular curve, that means it should be differentiable curve. On top of that, I want that derivative also should be non-zero if t runs from open interval a to b. Yes. Now you can say smooth means now since the derivative is non-zero, so therefore I can say that a curve is smooth. I can talk about the tangent, and the tangent should vary smoothly. Okay, if it is the case, so look, for smooth curves, unit tangent vector varies continuously. What does it mean? So for a smooth curve gamma, what is the definition of smooth curve? That means it should be differentiable, derivative should be continuous, and derivative is non-zero. Now if I have a derivative is non-zero, so I can have this kind of object. So what is that? So this is, I am defining capital T of t, which is z prime divided by absolute of z prime. Now you see, look at this one. This is a continuous function. Why? Because in the definitions of smooth curve, my curve, if it has a parameterization, say let it be zt, that means z prime should exist and z prime is continuous. So that means the numerator is continuous. And what is the denominator? Denominator is absolute of z prime t. And denominator, I can make sense of this object because z prime of t is non-zero, but absolute of z prime t, that is also a continuous function. Now cosines of two continuous functions, that is also a continuous function. So therefore this is a continuous function. T goes to t of t, it's a continuous function. So therefore it says that for a smooth curve, we know that this is non-zero, so and hence the unit tangent vector is well defined. So and with an angle, so the way I have defined with the angle argument of z prime of t. So this is z prime t is a complex number. So this is the corresponding with an angle of inclination should be argument of z prime of t. Now as the parameter t varies over the interval a to b, then the tangent vector turns on varies continuously, because it follows from the expression of your what is function tt, because tt is nothing but the cosines of z prime t divided by absolute of z prime t. Z prime t is continuous, absolute of z prime t is continuous, so cosines of two continuous function is continuous. So therefore my tangent functions t goes to t of t, it's actually continuous. In other words, if I look at pictorially, look, so this is a very nice curve. So this is my curve, right? And it is a what is called simple curve or smooth curve. Why? Because look, so if I draw a tangent, I draw a picture, so this tangent, it varies smoothly. Smoothly means it varies continuously. And so this is the way I have kind of figured it out. So therefore this is the corresponding arrow. If you see the small arrows, they vary very smoothly along the curve. That means your curve should be very nice. So that means I can have this kind of things. It is a smooth curve because if I have a tangent there, of course smooth means what? It is differentiable, derivative is continuous, and my tangent varies very smoothly. So for example, like the circle or say straight line or say parabola, these are all smooth curves. Okay, so smooth curve is one of the unit tangent vector varies continuously, because the definitions you have from the definitions of smooth curve, it automatically follows. Okay, so now I come to the definition of what is called contour or piecewise smooth curves. Now if from the definition, so contour means what? This is actually piecewise smooth curves. Smooth curves I have defined. Piecewise smooth curves means what? It is actually smooth, but it is not all the point. That means I can somehow break my curves into finitely many pieces, and each piece should be smooth. That is the meaning of what is called piecewise smooth curves. Okay, so that actually follows from the what is called the way I have defined, like smooth curve and piecewise smooth. That means it is not smooth fully, but I can break my curves into finitely many pieces, and each pieces should be smooth. What is the definitions? So and that's I'm saying that is the definition of contour. So a contour or piecewise smooth curve is a curve, okay, consisting of finite number of smooth curves joining end to end. So that means this is a smooth curve, okay. Suppose it starts from here, it ends here. Then I am starting with another smooth curve which starts from where my earlier one ends. Okay, so this ends here, and the next one C2 is started from here. So C2 will end here. Then I will join another smooth curve, so let it be C3, whose joining point should be the end point of C2. Similarly C4. So in other words, I can say that if I look at this curve as a whole, right, then I can break this curve into 1, 2, 3. Okay. So 1, 2, 3, 3 pieces I can put it where each piece is smooth. This is smooth, this is smooth, this is smooth, and this is smooth. So therefore I can say that two ways you can define it. A curve is called piecewise smooth if I break that curve into finitely many pieces and each piece is smooth, or you can say that so it is nothing but the consisting of finitely many smooth curves where one smooth curve end and the other smooth curve starting point there. So that should be. So it says that is a curve consisting of finite number of smooth curves joining end to end. That means suppose if I have a smooth curve is starting from somewhere, end somewhere, and another smooth curve, it should start where the earlier one end. So it should be like that. Okay. So this is also a smooth curve. It has only one piece. So this is also smooth. For example, I can break this. So only you see the corner point, you lose the differentiability, right? Because it is a sharp corner, so you lose the differentiability there. So what you do, you just break this corner, and then you'll have these many pieces. This is one piece, this is one, and at each pieces they are smooth. So therefore, I can break my curve into finitely many pieces, and each piece is smooth. So therefore, it is called piecewise smooth curve. And next time I will say that piecewise smooth curve means it is actually contour. So I have certain examples. So any oriented polygonal path, circular path, these are all continuous path. Okay. Polygonal means what? It should be like this one. So these are the kind sharp point. There you lose the differentiability. So you just remove, or you can cut here, cut here, cut here, cut. So therefore, this is smooth, this is smooth, this is smooth, this is smooth. So 1, 2, 3, 4, 5. So it is a combination of smooth curves, but you have to want us to be careful that if I have this smooth curve, the end point, if it ends here, then the another smooth curve should start from here. So it is finitely many pieces of what is called smooth curve. So piecewise smooth curve means it is actually, I am saying that contour. So now next time if I say that let's this gamma be a contour, okay, then you can say that it is actually smooth but not smooth fully, it is piecewise smooth. Okay, so then another concept is coming, what is called opposite curve. Now opposite curve means what? So if I have a curve, it will have a parameterizations. If I have a parameterizations, so therefore if I have the domain from A to B, so let me just give me the different definition, then it will be clear. So consider the curve C having the parameterization C is exactly equal to gamma t, which is xt plus iyt, t runs from the interval A to B. Then the opposite curve, I am denoting at minus C, but what is the definition? Look, it says that it traces out the same set of points in the complex plane, but in the reverse order. That means whatever the points in the curve C is there, minus of C should also have the same number of points, same set of points, but the direction will change, but in the reverse order, and it has the parameterizations, this kind of things. That means if C has a parameterizations gamma t, I am saying that minus of C will have a parameterizations, let it be zt, and it is like x of minus t plus y of I times y of minus t. Here t runs from minus b to minus a. Now this, look, so if I have these parameterizations, suppose C has a parameterizations gamma t, which is xt plus iyt. Suppose this is my what is called curve C. So that means what? If t runs from A, so suppose this is my capital A, which is nothing but gamma of A, and t ends at B, so this is capital B, suppose this is gamma of B. Now if t runs from A to B, that means this is my A and this is my B. So starting from A and then going towards B, then my points on the curves moves in this direction, starting from gamma of A, which is A, and then ends at gamma of B, which is nothing but capital B, and move in this direction. That is actually sometimes called natural orientations. So it starts from small a, that means gamma of A, and it ends up gamma of B, which is capital B. And the way t moves from A to B, it will give you a natural orientations or natural directions. My point should move along the curve C. So suppose this is the one. Now look at minus C. What is this? This is the corresponding parameterizations. Now look, see, if I take t is equal to minus b, then what is the value of z, the parameterization z of minus b? What is that? If I say this is nothing but xb plus iyb, because this is minus of t is there. Now xb plus ib, what is this? This is nothing but gamma of b. So that means I start with t is equal to minus b, that means the left hand point, I'll start with the point capital B. And what is the value t is equal to minus a? That means z of minus a. This is, you can calculate, this is xa plus I times ya. That means it should be what? Gamma of a. That means for minus c, the way I have defined the parameterizations, if t is equal to minus b, I am starting with the point B. And if t is equal to minus a, I am ending at the point A. And if t runs from minus b to minus a smoothly, then I am having natural way of my point should going along the curve. So therefore, if it starts from B and it will end at A, then it should move in these directions. So therefore, if the directions, natural directions of C is in these directions, minus C will have a direction in the opposite way. That's what I have written. So therefore, it's the same set of points it traces out for all the points here, same as all the points here. But the main difference is that if it starts from A and end at B, so minus of C, it should start from point B and end at A. So therefore, if C has a direction in these directions, minus C will have opposite direction. That means if C starts from capital A, end at capital B, minus C starts at capital B, end at capital A. Okay, that's exactly how I have written. So traces out the same set of points in the complex plane, but in the reverse of order, and it is the corresponding parameterization. So another picture I have given, suppose this is my C, it starts from Z1 of A, one parameterizations in at Z1B in these directions, minus of C will start from here and come back to here. So if I write the parameterization as Z2, so Z2 of minus B is exactly equal to Z1 of B, and Z2 of minus C is exactly equal to Z1 of B, but it should be in the reverse directions. So one example I have given, suppose this is a circle, so this is 2 times e to the power it, right? It's a circle of radius 2, okay? So that means if I draw a picture, so this is circle, this is my radius 2. So therefore, if it starts from say 2, 0, and if it moves in these directions 0 to 2 pi, then it will end here. Then what is the parameterization of minus C? So it will start from here, but this time it will go in this direction, reverse directions. So you just use the parameterization. So minus of C, ZT 2 cosine of minus T plus 2 sine of minus T, because this is the definitions. This is 2 cosine T minus I times 2 sine T, but this time T runs from minus 2 pi to 0. So therefore, if I draw a picture, you will see it will start from here, but this time it will move in these directions. Okay. So that means it will have the same, like traces the same set of points, but the directions will be opposite. Yeah, so I think I should stop here. So later on you will see, now I have the definitions of opposite curve. So now next time I will talk about what is called the orientations. So as I said, I already discussed, so given a curve with a parameterizations, it will have a natural orientations. And if the natural orientation is one direction, opposite curve will have the what is called opposite orientations. Maybe in my next class I will talk about that orientations, okay, and then I will talk about what is called contour I have talked about, okay. Then of course contour integrations or line integral I will talk about, and then I will discuss one of the kind of fundamental theorem in complex analysis, that is called Cauchy-Goussard theorem. I think I will start with the orientations of my smooth curve in my next lecture. I think I should stop here. Thank you.